Right, welcome to part 2. So what we're doing here is again just controlling this LED light over here based on these numbers. So if I draw just a very straight circuit to this LED here, so we're going to control this LED whether it turns on or off, or whether it's true that it's on or it's false that it's on, based on a logical circuit that we're going to draw over here. So we're going to have 4 inputs. We're going to have A, B, C, and D, like so. And so we're going to have some inputs into some gates, and C we're going to have C going through a NOT gate right here, and then both of these are going to go through an OR gate. Again, apologies for my pen being so messy like this. It's just very sensitive when I lift it up from the drawing tablet. A and B are also going to be going through an OR gate, and then both of these OR gates are going to be going through, well, you guessed it, another OR gate like this, and we're going to have the output from this last OR gate go directly to the LED light. Now, if we just take a random number from these numbers over here, so let's take, for example, number 7, we're going to put the 0 into A, the 1 into B, the third one into C, and the last one into D. So we have AB going through an OR gate, so it's 0, 1, and if we look at the OR gate over here, 0, 1 yields a positive, a true output, a 1 output, so the output here is a 1, and then we have C down here, which gives us a 1 going through a NOT gate first. So the NOT gate, if we look at the NOT gate here, if the input is a 1, the output is a 0, so it becomes a 0 like right here. And then we have a 1 going through D, so we have 0, 1 going through this OR gate here. Again, 0, 1 gives us a 1 output. And then we have a 1, 1. So notice that the outputs for these two gates become inputs for this gate over here. So we have a 1, 1 going through this OR gate, and we're going to look at the truth table here. 1, 1 gives us an output of a 1, a true output. So the output is a 1. So that means that there will be electricity flowing through here. So it's going to allow data to flow through, and then it's going to turn this LED light on with the number 7. And if we look at the number 7 here, we can see that clearly this LED light is on for number 7. Now these other LED lights in the number will have their own logic gate circuits that control their output, but this circuitry here belongs only to this LED light right here. Now we're going to use the same logic gate circuit, and we're going to try the only number which should yield a 0 output at the end here. So we're going to take the number 2. So we're going to have 0, 0, 1, 0, which is the number 2. So 0, 0 going through an OR gate. We look at the truth table. 0, 0, the output is 0. And we have a 1 going through a NOT gate. So if we look at the NOT gate truth table, an input of 1 gives an output of 0, like so. And then D is a 0, so we have 0, 0 going through this OR gate. And then the same thing here, we have 0, 0 going through this OR gate, which basically means that this LED light will be off when the number 2 goes through this logic gate circuit. So we can see here, number 2, this LED light is off. So this is how logic gate circuits control the flow of data based on their makeup, and you can make billions and billions of different logic gate circuitry depending on the ones that you decide to use. Alright, so let's look at the next slide right here. So the type of questions you might get in the exam may differ, but just pay attention to the wording or the symbols that they're using, and you'll be able to get this very, very clearly. So if we have a look at question 1 here, they might ask you to convert or to develop a logic gate circuit from this equation right here. or this expression, excuse me. So we have two inputs, we have A and B, so we're going to say A and B like this. And A is a NOT gate first, so A is going through a NOT gate first, and the same thing is happening for B. So we're going to put both of these two inputs through a NOT gate, and then they're both going through an OR gate right here. So we're going to be able to draw this like that, and then there's your output. So this is the logic gate circuit for this expression over here. You might be asked to even create an expression using these symbols we talked about in the previous slide here. So these symbols right here. So we have an OR gate here. So the OR is a plus, like so. And then we have two inputs, A and B. And then they are both NOT. So we put this little line on top of the two letters like that. Might look like a very cool haircut, but it's okay if you just stop it right there. Let me just draw it again so you don't get confused. You don't have to draw the little tail at the end. So that will suffice like that. So this is the same thing as this logic gate circuit here, as this expression over here. And if we look at the next question here, same concept. They might ask you to draw a logic gate circuit. So we have A or B. We know this is an OR because we said that the plus is used for the OR gate. So we have A and B. So A and B going through an OR gate like this. And then we can see that they join up. Both of also the output for this gate is connected through another gate which has C as an input as well. So we have C like so. And both of these are going through, I'm going to let you try and guess what gate is this. If you said AND gate, you are absolutely correct. So the dot is for the AND gate, and we're going to do an AND gate symbol like this. There we go. So this is the logic gate circuit, which is represented by this expression over here. Now don't forget, you might also be asked to draw or to come up with an expression like this based on a logic gate circuit like the one below. So in the exam, you might not see this up here, you might just see the circuit, and you are asked to create an expression from this down here. So I would start with A and B first. So A, B, and I can see it's an OR gate that is controlling that data flow. So I'm going to put that plus right here. And I can see that this, the output for this gate, is calculated first. So I'm going to put brackets around this. So this calculation is done first. And then I can see that C joins up with the output from that gate through an AND gate. So we have AND C like that. So this will get calculated first. So whatever the output for this is, will then go through an AND gate with C, like that. Now if C had, for example, this symbol up here, which is the NOT gate, then C would be going through a NOT gate first before it goes into the AND gate. But if this symbol up here was covering the entire of the expression, then that means that the NOT gate would be on the other side of this because it's controlling the output of everything like that. You might get a question like this, like question number 3, that says, Kelly has a chainsaw which has 2 buttons. Because of safety, button 1 and button 2 must be pressed for the chainsaw to turn on. So if Kelly presses just button 1, the chainsaw won't actually turn on because of safety. So, you know, the manufacturer has put the safety feature in the chainsaw so that people don't have accidents, and they can only turn it on if they're holding the chainsaw with both hands, because that means that they're aware that they have the chainsaw, and so on and so forth. So both button 1 and button 2. Now, regardless of what the context of the question is, you just have to pay attention to these keywords like this one right here. And as soon as you read that, you'll be aware of what gate to use. So if we were to draw an expression of this, an AND gate would be just a dot, and button 1 would be input A, for example, and button 2 would be input B, like that. And if we were to draw a logic gate from this, then it's very simple. We have a logic gate like that. So we have the output, we have the two inputs like this, and there it is. Okay, so I hope you enjoyed this. Any questions, please email me and we'll get through it. All the best.